Good evening, students. So basically today I'll be concentrating on kinematics, and basically the study of graphs between displacement versus time, velocity versus time, and acceleration versus time, and how these are interrelated, and how we can study them to solve basic rectilinear problems, right? So see, I'll start with a basic example. Suppose you are driving on a road. Okay, in a car, and let's say that road is busy. So it's pretty obvious that the velocity of the car will not be the same. Okay, so let's say that velocity ranges from 0 to 50 km per hour. Okay, now if I tell you to calculate the average velocity, okay, that is, I think, pretty straightforward. What we do is we take some displacement. Let's say delta x is the displacement of the car, okay, and we calculate the time taken by it to travel this delta x. Thereby I'll get the average velocity. But instantaneous velocity is not that straightforward. Also, it is not that intuitive. Okay, but while sitting in the car, it's pretty obvious. If we look at the speedometer, the velocity does not remain same. So to a certain extent, that speedometer reading gives us the instantaneous velocity. Now how to calculate in mathematical terms? See, what we want to do is we want to calculate the velocity at each and every point. Okay, that means that this delta t, okay, delta t will be infinitesimal. Okay, so the rate of change of displacement in very small interval of time, thereby will get the tangential, or we call it instantaneous velocity. So we define mathematically something like this: if delta t tends to 0, what we get the rate of change of displacement, that is our instantaneous velocity. So that is the velocity at a particular instant. We also write in terms of dx by dt, that is infinitesimal change in time. We are having this infinitesimal change in displacement. Thereby we are getting a instantaneous velocity. Okay, the thing is, over here, this instantaneous velocity is pretty important if we want to study the graphs, because what we know is instantaneous velocity, as we have seen over here, is given by dx by dt. Similarly, instantaneous acceleration can be given as dv by dt. These two relations have to be kept in mind very carefully in order to understand the basic graphs. Okay, so we'll study our analysis. So let's take a very straightforward problem in the sense of rectilinear motion. Let's say over here we have ground, and what I am doing in, I am projecting a ball of mass m with initial velocity u in the upward direction. Okay, and obviously we have gravity. So first of all, this will be a rectilinear motion. This ball of mass m will go up. Okay, it will reach some maximum height. Let's say it reaches over here, that is h max. At this point its velocity will become 0, and then it will come down. Okay, as it comes down, its velocity increases. Okay, now over here we can say that since acceleration is only g, for the first half of the motion, actually the body is retarding. It is starting from maximum velocity, and then velocity is slowly becoming to 0, and then actually velocity changes direction, and speed continues to increase in the later part of the journey. So if I tell you to draw the graphs of acceleration versus time, velocity versus time, and let's say displacement versus time. Now we'll start with acceleration versus time, and as we progress, I'll tell you how they are pretty much related. Okay, now we have to keep in mind these two relations, that velocity, instantaneous velocity, is given by dx by dt, that is instantaneous change of displacement with respect to time, and acceleration is given by dv by dt. Okay, now over here if we start with A versus T or with any set of graphs, the most important thing is we have to consider what point we are taking origin, okay, because our graphs will be according to that. Conventionally, where the body is starting at t is equal to 0, we consider our origin. So over here we are considering origin over here, okay. So as see, it's a rectilinear motion, so we have to be concerned with the upward direction, and let's say I am taking upward direction to be positive, okay, so downward direction will be negative. These type of conventions has to be taken care of in order to draw the graphs properly, okay. So we start with A versus T. Over here we see that during the whole flight, during the ball going up and then coming down, the acceleration is not changing, because acceleration due to gravity, if we consider at a height h, which is very small as compared to the radius of the earth, we say that acceleration does not changes. Therefore acceleration due to gravity remains constant, okay. And since I am choosing my downward direction to be negative, and over here acceleration is pointing towards the downward direction, therefore it will be something like this. Its magnitude will be 9.8 meter per second square, okay. And as I see, as time passes, this does not change, right. Let's draw two time intervals t1, 0 to t1 and t1 to t2. 0 to t1 represents ball going up and reaching a point h, that is the maximum height, okay. Then it will come down, it will take same amount of time, okay. Now let's move on to v versus t. Over here we know that acceleration remains constant. Acceleration does not depend on time, it remains constant, okay. Therefore what we can say is this dv by dt has to be constant. That means that the slope of v versus t curve has to be constant, because that is nothing but the acceleration. So we are sure that that has to be a straight line, okay, with some constant slope, inclined line, okay. Now the other thing is our upward direction is positive, okay. Therefore velocity, initially velocity is maximum and velocity is decreasing as this particle is moving up. So we know that at t is equal to 0, my velocity or the speed will be maximum and it will be in the positive direction. So at t is equal to 0, I have to start with some initial velocity, and as time passes I know that velocity will decrease, okay. The other thing I know that at the highest point the velocity becomes 0 and the rate of change of velocity is constant, so it will be a straight line, okay. So this is for 0 to t1. Now in fact for the whole journey the slope of v versus t cannot be different, it has to be a unique value, because acceleration is a constant. Therefore for rest of the journey slope has to be the same, but after the topmost point velocity is changing its direction, okay. The thing is initially it is 0 at the topmost point, then velocity will be pointing in the negative direction, okay, but the magnitude or the speed will keep on increasing, okay. And since I told you the slope remains constant, we'll have this kind of a graph between t1 and t2. As you can see that slope has to be constant and slope is constant. So this is the another hint that v versus t has to be a straight line, okay. Now if you look at v versus t and try to draw displacement versus time, remember these all are vectors, okay. If you try to draw displacement versus time, okay, initially I am taking displacement to be 0 when it is at the ground, okay, and since it is moving in the positive direction displacement is increasing in the positive direction, this we know, okay. But the rate of change of displacement over here is not constant, okay. Remember this, over here dx by dt is not constant. Why? Because dx by dt is nothing but the velocity, and velocity is not constant. As we can see that velocities have multiple values for different time, okay. Therefore first thing is clear that slope cannot be constant, okay. That means that it cannot be a straight line, because straight line has a unique slope. Therefore there has to be a curve, okay, with different slopes. Now how to find out that what should be the curve? Again that will be given by how the slope is changing, okay. Over here as we can see that slope initially is maximum, okay, and positive. So we know two things, and as time passes what's happening is the slope is or the velocity is decreasing, therefore the slope has to decrease at the midpoint, okay. When the particle is at the topmost point the slope has to be 0, okay. So initially the slope is maximum and then it is becoming 0 at t1, okay. So let's try to draw graph between 0 to t1, okay. Initially the slope is maximum, okay. Therefore it will be something like this. Okay, as you can see that the slope is given by, slope at a point is given by tangent at a point. Okay, so as you can see, the steepness is decreasing as we move from 0 to t1, and this should happen because over here the velocity is decreasing and slope is nothing but the velocity. Okay, so over here the velocity will be maximum, and as you can see that velocity is decreasing. And what is happening over here? Same thing, the velocity is decreasing as it is moving up, and at the topmost point the velocity is 0, therefore slope will be 0. Now try to analyze the motion in the second half. See, in the second half what's happening is, after this point it will start moving in the opposite direction. Okay, and velocity keeps on increasing. Okay, therefore what we can see is the displacement will decrease. And what about the slope? See, if you consider the speed, you have to worry about the steepness. Okay, don't have to worry about whether the slope will be negative or positive, just have to worry about the steepness. Okay, so what we can say over here is the steepness will increase because speed is increasing. Okay, but the thing is slope will be negative because velocity is negative, right? So as you can see over here, the slope is getting steeper and steeper. Okay, so and another thing is the displacement is 0, and it has to be 0 because it is returning finally back to its original position. So displacement has to be 0. Okay, so basically these all graphs are interrelated. Okay, and if you understand the relationship between the graphs, it will be pretty easy to draw. Okay, one similar example we can take so that we just understand the topic fully. Okay, so let's say from a height h, now I am dropping a ball, okay, with initial velocity 0, right? So under the action of gravity, now it will gain velocity, and let's say at the bottommost point that is smooth. Therefore after rebounding, its velocity will change direction. Okay, but the speed will remain same. Okay, so it will come down and then it will go back up to the same height. Okay, so it's basically another rectilinear problem, and we would like to draw again x versus t, v versus t, and a versus t. Okay, our choice of positive and negative remains the same, and origin, as see, origin we always take whenever the particle is starting or whenever we are considering t is equal to 0. So over here I am counting time from moment when the ball is about to drop. Okay, so that is t is equal to 0, and that is also the origin. So if we start with a versus t, again acceleration does not depend on how this object is moving. Okay, acceleration due to gravity is always downwards, and if you choose downward axis to be negative, acceleration due to gravity again will be 9.8 meter per second square. Okay, it does not depend on whether the particle is moving upwards or downwards or whatever. The thing is over here, since negative direction is in the downward direction and gravity is downwards, therefore over here the acceleration will remain negative for the entire interval of this motion. Okay, therefore another hint over here is the velocity versus time has to have constant slope, because acceleration has a same value. Over here acceleration is constant, therefore slope will be constant. dv by dt is given by acceleration, as we know. Okay, over here another thing is it is starting from rest, so initially the velocity will be 0. Okay, and since downward direction is negative and it is moving or gaining velocity in the downward direction due to this acceleration, actually the velocity increases in the downward direction, or we can say that speed increases. Okay, so will it go upwards or downwards? It has to go downwards, because this negative direction is downwards and it is moving in the downward direction with increase in velocity. Okay, so this will for the half of the journey, that is 0 to t1. Okay, for see, this is the point when it is about to strike the ground. After that what will happen is the direction of the velocity changes. Okay, but over here since the surface is smooth, the speed remains constant. Okay, so over here what will happen is the magnitude of the velocity, that is speed, will remain constant, whereas the direction of the velocity changes. So the graph will jump from here to here. Remember this magnitudes, let's say that is v1, will remain the same, that is minus v1. Okay.